Dear all participants, we would like to ask you to turn off your microphone, turn on your camera, and use virtual background. Webinar will begin shortly. Good afternoon, ladies and gentlemen. Welcome again to webinar series eTalk 13, Clean Energy and Advanced Material. Today, October 9, 2024. This webinar is supported by Indonesia Fuel Cell and Hydrogen Energy, IFHE, in collaboration with National Research and Innovation Agency, BRIN, especially Research Group Fuel Cell and Hydrogen Material from Research Center of Advanced Materials. We would like to welcome our speaker, Dr. Matthias Kessler, Product Manager in Venio, Chemist and Application Specialist from BOPT and Ettlingen, and Dr. Dan Wu, Business Development Manager, Physicist and Application Specialist, BOPT Ettlingen, and also Ibu Rizkia from Novatech as moderator. And also welcome all participants. We also thank to our sponsor of this webinar series, Astra International, Bruker, Novatech, PT Era Mitra Perdana, and PT ITS Science Indonesia. Well, before we continue, we will listen to opening speech. Will be delivered by Professor Dr. Enia Listiani Dewi as President of Indonesia Fuel Cell and Hydrogen Energy. Please.
Hello, welcome to Indonesia Fuel Cell and Hydrogen Energy webinar series. At this moment, I visit Tokyo University at the Laboratory of Energy Conversion and Photocatalytic. And we are look around of the utilities of the Raman, of the IR, GC, Gascro, and so on. So it is really related to our webinar series today. And I almost welcome to all of the speakers, and also welcome to the member of IFHE that creating many issues that really interesting regarding to the hydrogen and ammonia development and the use of the those in the energy sector. So we are also discussing about the ammonia synthesis. It is really interesting that we can create the hydrogen from the water using the electrolyzer, and then we can also make a synthesize by the heat reaction with the nitrogen from the air. So that's what my friend Dr. Ella that doing at this Tokyo University. So with this webinar series, hopefully you are all would be very interested on the energy sector, and we are knowing that Indonesia now also have focusing our policy development, our research development on the hydrogen and ammonia, and we are know that in the net zero emission in 2060, we will have more than 45 gigawatt of the hydrogen that we can create from the electricity. And that would be a very huge demand in Indonesia. But comparing to the renewable energy resources that we had now, it is still many space to develop to creating the hydrogen, to produce the hydrogen and ammonia. So we think that Indonesia would be a good hydrogen hub for the global ecosystem of hydrogen and ammonia development. So we are really happy to have you all here, and we have sharing our knowledge and our experience. So thank you so much to joining this webinar series. Hopefully we can see you again in the next topic. See you.
Thank you, Professor Enia. Before we continue to our session, I would like to ask for a photo group. So please, all participants, turn on your camera. You can put your best smile and please committee help us to take picture. Okay, I will count down or start from the first page. 1, 2, 3. Okay, and then next page. Okay, 1, 2, 3. Okay, next. 1, 2, 3. Well, I think it's enough. So, before we start the presentation and discussion session, I would like to remind our participants that committee has already prepared some door prize for active participants with the best question. So please, during the session, you can write your question in chat column or raise your hand during question and answer session. Well, without further ado, please allow me to invite our moderator, Ibu Rizkia. Please, Ibu Rizkia, time is yours.
Yes, thank you, Mrs. Dewi, for the opportunity, and thank you for Brain, IFMHA, for holding this webinar, and also all participants to join this seminar. So, good afternoon, everyone. My name is Rizkia. I'm from PT Novatech Integra Solusindo. We are sole agent and distributor broker in Indonesia, and I will be the moderator today. Before we begin, I would like to introduce our presenter. We have two presenters today. First is Dr. Matthieu Kebler. He is product manager in Venio, chemist, application specialist in BOPT Esslingen, Germany. And for his background, he studies chemistry and achieved PhD at Albert Ludwig University in Frankfurt, worked at biggest university in Wuppertal, and his focus research in inorganic and analytical chemistry. And focus for today's presentation is energy storage research using FTIR and Raman spectroscopy, and then insight into catalytic reaction by in situ spectroscopy. And then for the second presentation, we have Dr. Dan Wu. She is Business Development Manager, Physics Application Specialist in BOPT Esslingen, Germany. She's background in studies condensed matter, physics, and achieved PhD at Chinese Academy of Science in China. She worked at FEH postdoc at Stuttgart University in Germany, and she's focused in high-end FTIR solution and application. And for focus of the presentation, she will explain to us about passive radioactive cooling material characterization by FTIR spectroscopy and hydrogen storage by means of catalytic hydrogenation, mechanism study by in situ drip spectroscopy, and greenhouse gases monitoring by ultra high resolution FTIR. So we're not waiting for long. So please start first presentation by Mr. Kebler. Please welcome and start your presentation.
Yeah, hello. Also, welcome from my side, from Germany, Ettlingen. And I will start the first topic. So this is about energy storage research using FTIR and Raman spectroscopy. So to begin with it, we can ask us, of course, the question, so what will power the world in the future? And for sure, it will be renewable energy. So of course, solar, wind, hydro, geothermal, and biomass energy, which is produced. But we also need storage capacities for that. So the energy needs to be converted to be then available on demand later on. And this can be done in different ways. Of course, we can use battery systems for storage. So this is a growing field and it's very interesting. And we can use chemical conversion to convert the energy into fuels. for example, hydrogen to use that later on. And then there are other storage systems like compressed air energy storage, pumped hydro, thermal energy storage, gravity energy storage. But we will focus in this talk on batteries and on chemical energy storage systems. And they are, of course, then key to unlock the full potential of renewable energy. So that every time if there's a demand for energy, then we can get that from the energy storage systems. And we can produce at any time new energy and store that in the energy storage. If we have a look at projections of the energy storage installations on the left side here, in the next years, we will see that it's projected that we have a tremendous increase of the storage systems and the capacity of the installations. And this is true for all over the world. If you have a look on the right side, on the operational energy storage technologies which are active, then at the moment the majority is still pumped hydro. So the energy is stored in water and this is pumped up into seas and then released to get again the energy out. But of course, there's also the others, so fuels and battery systems, and this field will increase highly in the future because we get a better conversion out of these systems in comparison to pumped hydro storage. So now what can we do with FTIR and Raman spectroscopy in the field of energy storage research? And there's a lot of possibilities for that. In the first part of the talk, we will focus on FTIR spectroscopy, and we can use that in different fields. So, for example, for research in fuel cells. We can, of course, use it for all kinds of battery research, so lithium-ion batteries or other battery types. We can use it in the research field of synthetic or e-fuels, so that can be power to liquid, power to gas, electrochemical reduction of CO2. And then there are further fields, for example, redox flow batteries, but I will not cover that in this talk today. So on the right side, you see a cycle. So if we are able to convert CO2 from the air with renewable energy to your liquid fuel, for example, methanol, we can close the cycle and then we can achieve two goals. So we have a renewable energy source and we can reduce the CO2 content in the atmosphere. And on the right side here is shown IR spectra, and we have an additional axis. This is the applied potential. And then in an electrochemical cell, we can observe reactions over time with a changing potential. And then we can see how the CO2 is converted into organic molecules. And I will show that later in more detail. So what we use in FTIR spectroscopy is then spectroelectrochemistry. And what is this? So this is the combination of a spectroscopic method with electrochemistry. And this is, of course, true for all kind of spectroscopic methods. So UV-Vis spectroscopy, FT-NIR spectroscopy, Raman, also NMR, X-ray diffraction, and other technologies can be used in combination with electrochemistry. And this gives us the advantage to observe in situ the change of the molecules on the electrode surface. And so on the left side here in the picture, you can see the change in the IR spectrum over time with the change of the potential at the working electrode. And this can be done, for example, during charging and discharging cycles of batteries. So we can understand then the reactions which are going on during the charge and discharge cycles. So we can study reaction mechanisms We can analyze the electrolyte in batteries, the analytes, and the electrode surface. For that, we can use different setups, and I will show that in the future slides. And research fields which are related are the investigation of the solid electrolyte interface. So this is really where the electrochemical reaction happens. This is very important. Again, electrochemical reduction, for example, CO2 conversion, synthesis of electrofuels, and cycling of batteries. The first application example I want to present is an example from the battery research. We have here a lithium battery test setup, and this is with a organic redox pair in the solution. And therefore, the coin cell is placed directly on top of an ATR unit, and this unit is installed in the sample compartment of the FTR spectrometer. And then on top of the crystal, we have a window and then the cathode, and we can then probe the cathode directly during the reaction, during the electrochemical reaction in the cell. And for example, on the right side, then the resulting spectra is shown during the charging process and the discharging process. And then we see how the organic redox pair in solution changes on the surface of the electrode. So we can directly observe these reactions inside of a battery cell. And also the second example I want to show to you is related to lithium-ion battery research. And again, we have a cell which is set up on a ATR crystal. And this is now a cell with metallic lithium inside, so it has to be an inert setup without atmosphere access to the cell. And again, we use an ATR crystal on top, then the electrode is pressed, and between the electrode and the crystal we have our electrolyte. And this gives us the possibility to see all the changes of the electrolyte during the change of a electrical potential. And again, we see here on the left side the IR spectrum. And what we see is if we increase the potential, then we see that additional bands occur. And these bands are related to lithium, which is dissolved and then solvated by parts of the electrolyte, which is either ethylene carbonate or dimethyl carbonate. And this solvation of the lithium ions can be then observed directly operando, so in the process of the direction. So for such investigations, ATR, FTIR spectroscopy is a very useful tool. And we use for such experiments our benchtop FTIR spectrometer. So on the left side, you see our vertex spectrometer, our vacuum FTIR spectrometer. What we need to do electrochemical reactions in an FTIR spectrometer, we need to include an electrochemical cell in the setup, and therefore we have a reflection accessory. You see it on the left side for the vacuum version for the reflection accessory, and on the right side, this is for the purge spectrometers like the Invenio shown here on the right side. And in these cells, in these reflection accessories, an electrochemical cell can be introduced from the top. And we can then use different mirror sets in these accessories to create different angles of incidence. We can use polarizers, and we can use different window materials for ATR investigations, but also for reflection measurements on the surface of the working electrode. So different setups can be realized with this reflection accessory. And one important thing I want to mention in addition, of course, the best way to do such experiments is a vacuum system, because with that you can avoid the atmospherical contribution And you see it here in the IR spectrum. This is the spectrum of water vapor and CO2. And they show, both gases show very strong absorption in the middle infrared, so in the fingerprint region, and of course also in the far infrared, but the middle infrared is the most interesting part for our battery research investigations. And if we use a vacuum system, then we can avoid this contribution, and we have a perfect baseline and a very low noise and a high signal to noise ratio is then possible. In addition to our reflection unit, of course, we need a potential setup. We can work together with different vendors of potential stats. For example, here a Gamry is shown, and we can then synchronize both hardware setups. So we can use electrical triggering to synchronize the start of the reaction and the end of the reaction. And therefore, we can send either from the FTIR or from the potentiostat a starting PTL trigger signal, and also for the end, we can then send a trigger and receive it from the other hardware. And this is done in the Gamry sequence wizards, and in Opus for our FTIR spectrometer, we have a rapid scan editor, and with that we can generate easy methods for our electrochemical reactions. So we can define how many spectra should be created over which time, and also synchronize with the potentiostat. So this is all easily done in the Opus software from Bruker. How does the reflection cell look if we have a look inside? Of course, then there's our cell made of glass or Teflon or polyiether ketone, and we include in that our electrodes and our electrolyte. And then from the bottom, there's a optical window placed, which can be either silicon or germanium for ATR reactions. And then we introduce the IR beam from below to this window. It reflects internally and then goes to the detector. And so we are able to record IR spectrum during the electrochemical reactions. And we have the possibility to either measure only the electrolyte, then we place our free electrodes simply inside of the electrochemical cell, or we do surface investigations, and for that we can coat our ATR crystal with a thin metal layer, which is made of gold usually or platinum. And then this metal layer is connected electrically and works as working electrode. And with that, we have a surface sensitive setup and directly observe any changes on the working electrode surface. And this is very often used because these processes are the most important ones, so the electrode processes. And there's a third possibility how we can use the reflection cell. We can introduce a different hemispherical window, for example, calcium fluoride or barium fluoride, and then this is transparent, so the IR beam goes really into the cell. It's not reflected internally, and then it hits the surface of a working electrode and is reflected on that surface, and then goes back to the detector. And with that, we can measure also the surface of the working electrode, and in addition, the electrolyte in between the working electrode and the window material. So we have information then on processes in the electrolyte and on the working electrode. So this is called then the thin layer configuration. There are also accessories available from other suppliers. For surface enhanced ATR measurements, there's a very famous one. This comes from Pike, and this is the Jackfish spectroelectrochemical cell. And this is also intended for surface sensitive ATR measurements, where we place either a silicon or germanium crystal inside, or we use silicon wafers. And again, these crystals or wafers are then coated with a metal layer which works as working electrode, and then we can do our surface enhanced spectroscopy measurements with that. I want to show some additional examples, not only related to battery research. We have here the reaction of the oxidation of methanol, and this is then related to methanol fuel cells. And here such a thin layer setup is used where we probe the surface of the working electrode and in addition the thin layer which contains the electrolyte between the electrode and the hemispherical window. And this is a platinum electrode used as working electrode, and then we can see the reactions happening on the surface of this electrode. So we see how the methanol binds onto the surface and it's oxidized then to carbon monoxide, which is shown here with the orange bands. And the carbon monoxide is bound in different motifs to the surface. This can be either in a bridged way or a terminal way. And we can differentiate between these both binding motifs. And then a second oxidation appears and CO2 is then released from the surface. And also the CO2 is of course then visible in our IR spectrum. And if we use a vacuum system, then we are sure that the CO2 comes from the reaction itself and it's not a contribution then of the atmosphere in the lab. And these experiments were done for different working electrodes, not only platinum, so also some alloys were used for the reaction. So all atmospherical contributions, CO2 and water vapor, can be avoided with a vacuum spectrometer. We can also have a look at electrooxidation reactions. If we use, for example, a flow-through cell where the electrolyte is pumped through the electrochemical cell, we are able to do also ATR measurements on such a cell, and then we can observe the oxidation, for example, of ethylene glycol in the solution, and then we directly observe all the reaction products which will be created then. And we can then measure with different flow rates to optimize then our reaction conditions and to get the best results for that. So also such reactions with a continuous flow of our electrolyte, they are possible with the spectroelectrochemical FTIR cells. And also for the field of synthetical fuels, we can use such setups. In this case, the questions was if we can use isopropanol as a rechargeable fuel. And in that way, the isopropanol is oxidized in a PEM fuel cell, proton exchange membrane fuel cell, to acetone. And then we can use a chemical reaction, a transfer hydrogenation, to reduce the acetone again to our educt. And these processes can be studied then with FTIR spectroelectrochemistry. So we can study the oxidation process in the fuel cell on the electrode surface. So again, platinum is used in this reaction, and then we see in the IR spectrum the bands which are going down in this case are then the product which is created, and the bands which are going up in the spectrum, this is the educt, so 2-propanol, which is consumed. And then we can also use the polarization for the measurement and increase then our sensitivity on the surface. And if we use P polarization, you see here the intensity of our absorption bands is much bigger. So also for fuel cell research, spectroelectrochemistry is a very useful tool. And finally, I wanted to show the reaction of the electrochemical conversion of CO2. So finally to methanol then, but we can observe all steps, and the first steps are the conversion of CO2 to adsorbed as a carbonate, hydrocarbonate, and oxalate in solution. And in this case, we also use a ATR, surface enhanced experiments, on a copper layer, and the copper works as electrode material in this case. And then we reduce the potential. So we go to a negative potential and start the reduction of the carbon dioxide in solution. And this can then be tracked nicely with IR spectroscopy. And here you see the bands of the adsorbed products in the reaction. So this is carbon monoxide, which is also bound to the surface in this case. Okay, I hope I could show you that FTIR spectroelectrochemistry is a very useful tool in energy storage research. Now I want to show you that we are also able to use other technologies to have a big benefit in battery research. So now we're going away from FTR also to other Bruker technologies. And the first one I want to show is Raman spectroscopy. We can work with our spectroscopy applications on the complete value chain of battery systems. So the first start is mining. You can see here the cycle for the different fields in the value chain, and of course we can analyze lithium salts very nicely with Raman spectroscopy. And for that, we can use our handheld Raman spectrometer and directly do that in field or in the lab. And here we have different LCT pegmatite minerals, and we can study them and directly identify them with a suitable library. So this is, of course, easily possible with Raman spectroscopy. Then we can use microscopy to investigate cells, for example, the anodes of a battery cell. If you use a laser IR microscope, then we are able to measure very fast, to scan the surfaces very rapidly, so we can then investigate such a graphite polymer mixed anode electrode, and then we can see the contribution of the polymer over the surface and have a representation of that very nicely with a very fast measurement. So this is done then in 2.5 minutes, and you have the image of the complete surface. So this is very useful for electrode investigations of batteries. We can
Itu tanya ketuanya. Vincent itu keluar nggak? Tali asli.
I'm sorry.
Tali BH.
Can not only use FTIR microscopy or laser microscopy, we can also use Raman microscopy. And this is, of course, also interesting for electrode studies. For example, anodes, so we can investigate the intercalation. Or on the cathode, we can see the lithium insertion or extraction. And Raman is very useful if we have carbon-based electrodes, so graphite or graphene, and there we have the prominent absorption bands in the carbon structure, and we can then nicely investigate and see defects, for example, on the electrode surface. And this is done, for example, with a Centera or a nanophoton Raman microscope and a corresponding Raman spectroelectrochemical cell. We can also introduce a small compact FTIR spectrometer into glove boxes to do reactions and to measure reactions in inert atmosphere without contact to the atmosphere in the lab. And this is a very handy tool and can be used, and of course, in for all kind of investigations. So for cell materials to investigate the cell itself, packaging, recycling of batteries, and we can do operando studies with a compact system also in the glove box. And here is just shown the example of a FTIR spectrum of a lithium salt, again measured in the glove box, which is prone to water, so this cannot be good handled in the atmosphere in the lab. So we need a glove box. So we can investigate raw materials and that way packaging, recycling materials. So this is very handy. And finally, we can not only investigate solutions, so electrolytes or solids like the electrodes, we can also measure gases. For example, if we want to measure the gas which comes out of the battery during an incident, so if the cell is damaged, then we can use our infrared gas analyzers to determine which gases are present in the reaction gas. And of course, which critical gases, they can be either explosive or toxic. And this is very important for safety aspects of the battery systems. So this is also an important field. Okay, with that, I hope I could show you that in the energy storage field and in the battery research field, we have a lot of solutions using FTIR and Raman spectroscopy. And with that, it helps us to refine battery components and answers important questions for the development of new systems and the improvement of existing systems. And of course, for all your questions, I'm then available later on, and you can also, of course, contact us then if you need additional information. So this is the first part of my talk. Now I want to switch to the second topic. And this is insight into catalytic reactions. So we can use FTIR spectroscopy also to have a look into catalytic processes. And this is really interesting, again, for conversion to create fuels and to have really the possibility to optimize your catalysts for these reactions. For the start, we want to have a look at what in situ means. So in situ means on-site or in position. And so we measure directly in the same position where the phenomenon or the reaction is occurring. So in the same place without isolating our measurement from the reaction itself, which would then be an ex situ measurement. So we measure inline, online, and sometimes also at line, but this is not really then an in situ process anymore. But if we use inline capabilities to use probes, for example, or reflection measurements or diffuse reflection measurements, we are able to do in situ measurements for catalyst research. And operando is a similar term. It's more specific than in situ. It means in addition that the sample is changing under an external influence. And this can be temperature, pressure, electrical potential, or any other additional influence onto the sample. And operando spectroscopy means then the measurement is performed during the same time when the change of our sample is happening. And so it's a simultaneous measurement. And of course, all different kinds of of analytical techniques can be used for in situ or operando measurement. So it's not only FTIR, so it's of course also Raman, visible spectroscopy, yeah, X-ray photospectroscopy, X-ray emission absorption, small angle scattering, or X-ray diffraction. So all these techniques can be used to do in situ observations of our catalyst samples. And what brings an in situ measurement? It brings us the third dimension. So usually we just have a standard infrared spectrum, but with in situ measurements, we add an additional axis, and this axis is usually time. And then we observe the time and the change of the sample, which is induced by, for example, temperature, or voltage, by pressure, by the concentration change, by a magnetic field, or by a force. So this can be very different stress factors for the samples. And we can create then 3D plots of the measurement where we have the wave number axis, the time axis, and our absorbance, so the change of intensity of our bands. And then we can track nicely the change, so new bands appear or existing bands vanish, and then we can relate them to the product and the educt and have a full understanding of our reaction. So therefore, in situ spectroscopy is a very handy tool, and it's very often used in such research fields. And we can investigate then all things which are happening when the educt is reacting to the product, so to the transition state, for example, or steps in between can then be investigated. We have a very sensitive probe with FTIR spectroscopy. We are able to measure in a fast way. We do not have to intervene. We have a reliable technique, and it's very easy to adapt that to the reaction. So on the right side, you have seen downhill skiing, and the reaction path can be compared to such a parkour. So this was just for a better understanding of the reaction pathway. And we will handle two different parts. The first part is reactions in an external UHV chamber. So we will have a look at applications, on components, on examples of such reactions. And the second part is more a lab approach. So here we handle then diffuse reflection infrared spectroscopy. And here we can use drift accessories, which can be simply inserted into the sample compartment of an FTIR spectrometer. And then we can use reaction cells to create different temperatures and do our powder catalyst measurements then inside of such reaction chambers. So to start with the first part, of course, an UHV chamber, so ultra-high vacuum chamber, is very useful to have reaction conditions available at very low pressures, so ultra-high vacuum, and of course also low or high temperatures. And this is important if we want to study heterogeneous catalyst reactions, because we are able then to really change our settings in the chamber, the environmental settings, and measure at different settings to characterize the catalyst properties. We can also use it to measure, and understand atomic layer deposition reactions. We do in situ measurements of catalyst model systems. We have the possibility to measure microstructured surfaces, and this is all very important for material development or catalyst design. And often, or almost ever, these UHV chambers are designed in a way that we can apply different spectroscopic measurements. So then it's mostly not only FTIR, but also, for example, X-ray spectroscopy techniques in addition. How does such a setup look like? We have our vacuum spectrometers, which is the Vertex 80V, for example, shown here in the center of the slide. And we can adapt to it chamber adaptation, which consists of two parts. We have then two chambers. So one has a mirror optic which focus the IR beam onto the sample, and then a second one which receives the reflected beam, and then a detector is placed in the second sample and then detects the sensitivity, the intensity which comes from the sample. And we do a reflection measurement. So this is a IRAS measurement, so infrared reflection absorption spectroscopy. For these kind of techniques, it's important to understand that if we have not a perpendicular incident of our light to the sample, but instead a certain angle of incidence, then of course the measurement spot is elongated in one axis, and yeah, this depends on the angle which is used. For example, for 80° of incident, we have an elongation with a factor of 6 for the y-axis in this case. So we have an elliptical measurement spot. And of course, this spot has then to be designed in a way with the corresponding focal mirrors to really cover the sample size of interest. I want to show you two examples for such an UHV adaptation. So on the right, you see the picture in the lab in Germany, in Jena. And in the center, there's the UHV chamber. We have different systems attached to it. And for us, the interesting part at the moment is here the FTIR spectrometer on the right side and the detector chamber on the left side. And the beam is then guided from the FTIR spectrometer upwards with a mirror optic, and then it's guided inside of the chamber. There it hits the sample at a very low pressure, and then the beam is reflected and goes to the detector chamber. And we are very sensitive with such measurements, and such ultra-high vacuum measurements can also be used, for example, for astrochemical reactions. So we can see conversions of cosmic grains with ice layers in astrophysical environments, and then how organic molecules are formed out of it. So this is all possible with such setups. Of course, they can also be used for all kind of catalytic studies. So an IR spectrum of such a conversion is shown here, and you see the absorbance value on the axis, they are really low. So this is a measurement with a very high sensitivity on the surface. And of course, we are able to adapt such installations to the needs of any customer. And here, the height difference is bridged with an additional optical part in the setup. A second example, this is also a IRAS reflection measurement in Berlin in Germany. This is used to investigate reactions on ice, vapor, and liquid vapor interfaces in a reaction chamber. And in this installation, we have to bridge very long ways from the spectrometer to the chamber and to the FTIR spectrometer and also to the detector chamber. And of course, this can also be realized. And for that, we use a intermediate focus at 2 positions. And with that, we are able to use a very long beam path to access then our UHV chamber. So you see, this is a very big installation. You can achieve the very special conditions in such reaction chambers. And of course, it's easier to do a IR measurement on the sample compartment of the FTIR spectrometer. And for that, so for standard lab approaches, we use then our drift accessories. So this is then the second part of this talk. We will have a look on the drift accessories, on different instrument configurations, and on possible applications for drift experiments. What is drift spectroscopy? So it's diffuse reflected infrared spectroscopy. So we have the incident light, which hits our sample, which is a powder usually. And on the powder surface, the beam is not reflected specularly, but instead it's reflected diffusely, so in all directions. And this means we need a optic which is able to collect the diffuse reflected light, and this is usually done with a big spherical mirror. And with this technique, we are able then to analyze rough surfaces of powders. We can observe the direction if we use rapid scan spectroscopy. We can investigate absorption processes of gases on the catalyst, the conversion then of the gases to the product. So this can all be studied, and we have information about the kinetics. And of course, this technique is then very interesting for catalyst development, so the improvement of existing systems, and is often applied in industry and also in university research, of course. Usually this is done then by material scientists, chemists, or process engineers. On the right, you see accessories which are available for fast drifts measurement. This is the easy diff. So this is for studies on standard environmental conditions, so room temperature, standard pressure in the atmosphere. And then we have the Herrick praying mantis reflection accessory for drifts measurements. And here we can insert different reaction chambers. So we have reaction chambers for low temperature measurements, which is shown here in the center, where you can cool down to minus 150 degrees. And we have a high temperature reaction chamber, which can be used up to 910 degree centigrade. And of course, we are also able to vary the pressure in these cells, so we can go up to a maximum of 3.4 megapascal with a high pressure dome attached to this cell. So these cells have 3 windows. 2 are used for the infrared beam, which incident and goes out here. And then 1 is available for observation, or if you want to shine, for example, UV light onto the sample to induce reactions. And here on the right side, you see the optical parts of the praying mantis cell. The beam comes from the FTIR spectrometer, is then guided via mirrors to the spherical mirrors here, and one guides the beam onto top of the sample, and the second collects then the part of the light which is diffusely reflected. And this has a special off-axis design, and this avoids that we investigate parts of the IR light which are reflected specularly from the sample. So we collect only the part of the light which is diffusely reflected. If we have a look into the inner of the cell, there we have our sample position. We place there a metal mesh, and on top of that we place then our sample powder. And of course, the reaction chamber can be used to change the pressure, to operate under vacuum, to change the temperature via control out of a special software, which also controls Opus. We have inlet and outlet ports. So these 2 can be used to let the gas flow over the sample. We can also let the gas flow through the sample, which if we use these both connectors, then the gas is flowing through the powder. And we can also use just the middle port here to evacuate the reaction chamber. And in addition, we have a connector for our temperature controller and two connectors to cool the housing of the reaction cell with cooling water. And then to have the best sensitivity, we want to avoid contribution again of the lab atmosphere. Therefore, we can purge the accessory with dry air or with nitrogen gas. And also we can install a special front cover to the accessory, which limits the accessible openings. And therefore we have a very good purge condition if we use then the reaction chamber with some kind of a purge shield and a purge shield slider. And I want to give you some examples, some measurements from the lab. We can do our in situ measurements in different ways. So this is the first possibilities here. We use a tensor system and we use repeated measurements simply. And the observation of the experiment is done for an ethylene polymerization catalyst. And then we see over time how our educt, so the ethylene is consumed, and then our polymer is created. And we can track this reaction over time. This is now here, the scale of the time axis is in minutes. So we track here the reactions slowly with repeated measurement. And of course, we need an installation of a gas handling system, and this is then attached to our drifts reaction cell. And we can also synchronize the walls for the gas flows with our FTIR spectrometer. If we want to have a faster observation of our reaction, we can change our spectrometer system to a system which is capable of doing rapid scan spectroscopy. This can be either the Invenio or the Vertex system. We have here also in addition a higher spectral resolution and broader spectral range. But for the in situ measurements, the rapid scan option is the most important one. And with that, we are then able to track reactions in a very fast way. And for example, this is shown here for the investigation of catalyst activity in a nitrogen oxide oxygen atmosphere. And then we see directly what is happening on the surface of the catalyst. And we see the formation of nitrite on the surface and also of nitrate in the bulk of the powder. We can combine these IR drifts measurements also with additional measurement techniques, for example, with X-ray measurements. So this setup shows you now a special cell where the dome is not only used for two beams of the infrared spectrometer, but also for X-ray beam, and then the scattered X-ray light is collected. So in this way, we have the possibility to measure simultaneously during the reaction the IR spectrum and with X-ray the pair distribution function. And this is done here for a sample, for a test sample, which is a complex, inorganic complex, and it's a hydrate. And the hydrate will release water over the time. And in the IR spectrum, you can see how the bands of the water are vanishing. So they are going down. So at 3,500, this is the water. And at 1,600, this is also the hydrated water. And these bands, go away. Then if we heat up the reaction sample. We can use drift spectroscopy also for gaze sensors. In that case, we can use, for example, tin oxide, which is doped with palladium. And we can use such reaction cells then to investigate the water or carbon oxide content on top of the powder sample. And in the spectrum here, you see again, if we go up with the temperature, how the adsorbed water is then removed from the sample. And in addition, we can see if we let gas flow over the sample, how carbon oxides, carbon monoxide or carbon dioxide is attached to the sample in the pores of this powder material. And now we are using for such investigations a vacuum system. As you have heard already, this has the advantage that we avoid any atmosphere contributions. So we are very sensitive in the regions, in the fingerprint regions, and also in the region where water vapor and atmospherical CO2 are, have an effect to our spectrum usually. There are other experiments which can be done in such cells. We can, of course, do a real reaction. If we have a titanium oxide precursor and react it with a nylon nanofiber, we can observe and track this reaction during the process. And finally, we are then able to observe the products. So our titanium oxide nanofibers and also the carbon dioxide, which is released during that process. And again, with a vacuum spectrometer, we are sure that this carbon dioxide comes from the reaction itself and is not a part of the atmosphere in the lab. And finally, as we can also use tungsten oxide as a gas sensor, and we can track what is happening on a tungsten oxide surface with such a drift reaction cell. And here we see the spectra, and you see only slight changes here in the baseline, and here bands are going down, and these bands are significant for gases which are attached to the tungsten oxide surface. And you see that if you use CO2, we can see really that two additional bands are occurring here. And this is only possible to see it if we use a FTIR spectrometer with a very high sensitivity in this region. And again, we use then a vacuum spectrometer for such observations. It's possible also to do the measurement not only in the purged sample compartment of the vacuum spectrometer, but we can also use a special front cover, and then we have the complete setup under vacuum. And with such a setup, we see that we can get a very good baseline. If we compare here the baseline of the measurement with the open system, with a purged system for 20 minutes and for 60 minutes, and with our vacuum measurement, we see that we can get rid of all the spectral bands which are coming from water vapor and CO2 in this case. And this allows us to do very interesting observations during reactions. For example, we can observe changes of the conformation of organic salts which are present on top of the catalyst powder. And then we can achieve measurements of shifts which are lower than 0.3 wave numbers, and we are still able to identify that with our drift spectroscopy. And similarly, such setups with a complete vacuum condition of the whole accessory and the reaction chamber, we can use for water gas shift reactions or for methanol steam reforming reactions, where we use a platinum aluminum oxide catalyst, and then we can directly investigate the bands of our resulting product in the fingerprint region and also in the CH stretching region. Okay, that was my final example, which I wanted to show to you. I hope you have seen that in situ spectroscopy, in this case, infrared reflection absorption spectroscopy or drift spectroscopy, are really useful to understand the processes in heterogeneous catalysis. And with that information, we are able to optimize reaction conditions and also all our existing catalysts. And I thank you a lot for your attention and for listening to my presentation.
Thank you, Mr. Kessler, for your presentation. Very detailed information regarding the process battery and then in situ monitoring about lithium. And we have 3 questions in the chat. Let me see. The first is Mr. Andiansa. He asked about the more energy and cost material and process for electrochemistry and energy storage create few major challenges for clusterization method. And infrastructure require new coordinate approach to everything for routing analysis is too sophisticated imaging and spectroscopy at national user facilities. What are your top approach to developed countries such as Indonesia to overcome those challenges to speed up the process? I mean, we this renew energy, so how he would like to know your insight regarding approaching the research.
Yeah, I think it's very important that we have a very good network also for collaborating companies. And with that, we are able to support not only for the FTR spectroscopy, but also for complete setups, for example, for catalyst research or for electrochemical setups. So we can then support you not only with the FTR part, but also we can suggest companies for example, for the potentiostat handling, and also in terms of UHV chambers, we can support you with the contact to the vendors of such systems, and then we can assure that the installation of such analytical setups in your labs is feasible from all sides, and that you get also the support from all sides to be able to do such experiments then in your labs.
Okay, hope at the answer. Do you copy about the answer? I mean, so the networking and collaborating is important if we would like to speed up the process and the research.
Yeah, so I mean that we can give you a full solution directly, not only the spectrometer, but we have also people experienced in these fields which can guide you. And if you tell us what kind of investigations you want to perform, then we are able to provide you with the best solution for that. And then you are able to start at at a higher level and do not have to prepare everything on your own. Yeah.
Pak Ardiansah mungkin mau menanggapi Pak dari jawabannya Mr. Kessler. Okay. Got it, thanks, she said. And we continue for another question for Mr. Harris. He said, please let me know how to set up the voltage in the FTIR analysis. Do you use an external equipment to change the voltage?
Yes, this is true. So we have additional hardware set up, and this is the potentiostat which is used. So this hardware sets the potential, and we use then usually 3 electrodes, which are then placed in the electrochemical cell, a working electrode, a counter electrode, and a reference electrode, and they are connected to the potentiostat, and with that we can, do the electrochemical part of the spectral electrochemistry experiment. And to add that, we can, of course, synchronize our spectrometer with this potentiostat, so which means we can control then the full experiment from one software. So we can either use Opus for that, or we can use the software from the potentiostat to control the experiment then.
Okay. Pak Haris, bagaimana memang pakai eksternal voltase Pak, pakai potensiostat, nanti tinggal Bapak adjust pengaturannya dan itu bisa, softwarenya bisa satu, kita punya software namanya Opus, itu bisa satu kesatuan, ataupun nanti softwarenya bisa terpisah. Ada feedback Pak Haris? Sorry, Chrysler, I mean, I answer in bahasa.
Hello, I'm Haris.
Yeah, Mr. Harris, please.
Yeah, thank you for the explanation. It's very clear. But let me ask one more question. Regarding to the cell, usually we use only small cell, but do you have a picture? So, I mean that how do you place the external source and also connected to the cell so that the equipment run well? Yeah.
We can provide you later on with a more detailed description of different setups where you have also drawings of the cell, and then it's perhaps easier to understand how big the system is. So usually we use kind of a milliliter as a volume for such a cell.
Thank you very much.
Thank you, Mr. Harris. We continue for other question. Mr. Budiman for that from DataMed. As far as I know, is that spectroelectrochemistry method still facing some issue with its application to microfluid system. Is it correct or it is been solved? Please. Regarding microfluid issue, is that solved?
Yeah, this is correct. So the available cells, they are made for bigger volumes or bigger flows. So for microfluidic systems, there's still development. So there's no final solution available at the moment to handle microfluidic spectral electrochemical setups or to do measurements with it. But there's evolution in this field, so I hope that soon such solutions will also be available.
Okay, hopefully soon we have solution for that. Mr. Bunyaman, is that any feedback from you? I mean, okay, he said thanks. Okay, there is 3 questions we already answered. Thank you, Mr. Kessler, for your presentation. And hopefully this presentation can make a very brief information for us forward. Thank you. And
Yeah,
we
thank you.
are, yes, thank you so much. We are continue to Dr. Danwu. Yes, our another presenter. Yes, please, Miss Danwood, to start the presentation.
So good afternoon. I hope you can see my presentation clearly.
Yes, clear.
Okay, great. So thank you everyone again for attending this webinar. So my colleague Matthias Kessler has introduced you many in situ and online solutions for the energy storage materials or reaction process monitoring. But actually what I want to deliver today as an information is that the FTIR spectrometer is not only for the energy storage measurement, but also it can be used for many other energy or green technique related topics. And it is a very fancy tool to do various measurement. And also, as you always think that, oh, okay, we should find the renewable energy, we should find the correct way to storage them, to store them. But also there's another section of this green technique is that the advanced material which can reduce the energy consumption. And this is also one important part of the green technique. And my first talk today is about the passive radial cooling materials. And this is the very advanced topic right now because once when this material, such kind of material is well developed, then it can be used for all of our daily life. And as you see from my first picture here, and if the house here is fully covering by the passive radial cooling material, then you will have no necessary to install air conditioning anymore. Yeah, so that's the idea behind it. And before I start with the theory part of the passive radial cooling, I want to show you this old, very ancient picture from 2,500 years ago. Yeah, and this is actually the ancient ice house in Iran, and it's called Yakchom. Yeah, and the purpose of this such construction is to store the ice at the inside of this buildings. And what they have is besides this dome-like buildings, there is a pool, water pool outside. Yeah, and for the and how it works and why in such a hot area in desert we can still have the ice available without any refrigerator, without any electricity. Yeah, and actually the principle is like this. So if you fill in the pool with all with the water, and then when the sunlight is shining on the water, and then it will reflect the light into the space, yeah, and it will absorb some light, but it will also reflect sunlight back to the space. And of course, in the atmosphere, you have many molecules, and it gets reflected uh, back and forwards, and then some of the light will again come back to the pool, but also some of the light will escape the atmosphere and go to the universe. Yeah, and in this case, the pool here is bringing the heat out of the building. Yeah. And in this case, inside of the dome, it will become cool or cooler and cooler, and no heat is actually generated or stored inside of the dome. Yeah. But actually, if you only see as such a procedure, you may lose a third dimensional of this principle. And this third dimensional is actually the wavelength of the light. And this is exactly the starting point of this passive radiative cooling materials. And here is another more clear picture of how this passive radiative cooling foil works. So here you see a house, and then if the sunlight is shining on this foil on top of the house, on the roof of the house, and then it will reflect the solar radiation back to the atmosphere. And in the meantime, there's another radiation also emitted to the space. But if you look at the wavelengths of this reflected sunlight and the radiation here, actually they are located in the different wavelength range. Yeah, and for the reflected solar radiation, it is mainly in the visible range. So it's in the short wavelength range. But for the thermal radiation, it's more in the mid-infrared range. And if you are counting with the Planck theory, and then you will see that the room temperature, like we have 30 degrees, 40 degrees now, and if we calculate this back to the wavelength range, it is exactly located at the mid-infrared range. So now if we take this third dimensional factor into the account of this material designing, then we have the clear goal to design a high reflected, a high reflectance material in the short wavelength and the high emission material at the mid-infrared range. And also, why this? Yeah, it's again based on the Kirchhoff law in physics. And in the Kirchhoff law, we have this absorbance of the material plus the reflectance of the material plus the transmittance of the material. And if we sum them up, it is the total amount of the energy. But now, if we can have very low reflectance and also very low transmittance of the material, then we have mainly the absorbance of the energy at the end. Yeah. And according to the Kirchhoff second law, we can say that the absorbance of the material is equal to the emissivity of the materials. Yeah. So in this case, we have the clear designing purpose of this passive radiative cooling material, which means that in the thermal radiative wavelength, which is the mid-infrared range, we should have low reflectance and low transmissions. And then that means we will have the high absorbance. And this is actually very often the case for the organic materials, yeah, especially for the polymers. And then in the short wavelength range, we can either have the low absorbance plus low reflectance, which means you will have the high transmittance. And this is called the ideal transitive radiative passive cooling material. Or on the other case, we should have low absorbance and low transmittance, but high reflectance in the short wavelength. And this is the ideal reflective passive radiative cooling material. Yeah. And how this distributed in the wavelengths, here I summarize for your information. Yeah. And then if we have such a material ready, then what effect we can get in reality. So here from this 3M manufacturing, they actually already developed such a very cost effective foils for the roof. And just imagine that you have this material on top of the surface, and then because it's bringing out the heat when when the sunlight is shining, then if you are testing the temperature of this area, you will have the cold or lower temperature of the area where this passive radiative cooling material is covered. And without the covering of such material, you will have higher temperatures. And then just imagine if now you have this material covered totally in your on your roof, and then that means no matter how warm or how hot in your area, I think this is also very often the case in the Southeast Asia area. And if you are having this material covered, then you probably don't have to use the air conditioning anymore. And this is the very good way and a very promising way to save the energy. Yeah. And as I said, for such a material development, you will have such a purpose or goal to achieve this high absorbance and in the mid-infrared and the high reflectance or transmittance in the visible range. And then when you're developing such a material, how do we prove it? Yeah, and this is the topic of the FTIR spectrometer at the end. Why? Because for our FTIR machine, as my colleague Matthias Kessler already introduced, it can cover the infrared range, the near infrared range, and also the visible range as a wide range spectroscopy. And this is the first advantage of the FTIR technique. And the second advantage of this technique is that you can combine with different methods to either measure, for example, the diffuse reflection, yeah, which means that the surface of the sample is not mirror-like. And also you can have our spectral specular refraction measurement with different angles. And this is also very often the case for the passive radiative cooling because the solar light is shining in from the different direction to the material. So the variable angle refraction accessory will be also be used or are very useful for such a material development study. And for the third one, it's also the emission accessories directly. Because for some of the materials, you may have the heating effect by either the environmental temperature or either with the very strong solar radiations and so on. So the temperature of the material will also getting a little bit higher than the room temperature. And then for such a study, you will need a temperature conditioning of the sample. So here it's also available as an accessory that you can measure the high temperature emissivity as well. So all these accessories with different purpose can be combined to the FTIR easily. Yeah. And so first of all, let me shortly introduce the integrating sphere where the material, the rough surface material is measured. And as also my colleague Matthias Kessler has introduced that with this rough surface, you will have one direction light introduced, but many directions scattered at the end. So with such an integrating sphere, you are able to collect all the light from all the directions. And in this case, you can analyze the hemispherical reflectance, the diffuse reflectance or diffuse transmittance if you put the sample into the beam path and let the light go through the sample. Yeah, and also you can calculate the directional reflectance at the end by substitution of the different parts of the reflectance. Yeah, and this is working also well for the full range. So for the gold coating integrating sphere, you can have the mid-infrared range and near-infrared range. And for the PTFE material, you can do easily to the visible range. Yeah. And here I have also a very nice examples for you. And this is the and if you have a FTIR spectrometer and you have the accessories in your lab, you can also do this as a practical experiment for your students. And the experiment itself is quite easy. So you can use the aluminum foil as the substrate, and then you can have two thick Scotch tape on top of the aluminum foil. And why this? Because the aluminum foil is actually a very good reflector of the light in any wavelength. And for the Scotch tape with enough thickness, it's polymer, so you can have a very strong absorption in the mid-infrared range. And this is exactly how we should design the passive radial cooling. And if you're interested in such experiment, you can contact me afterwards, and I can send you a very nice application note for such experiment. And this will be a very good reference for such a material study. Oops, I have this. Mm. Okay. And then also, as I said, the solar light is coming in from the different directions, and you are interested to study the different incident angle dependent reflectivities. And this is also available with the FTIR technique. Yeah. And here we also show a very nice examples that we scanning the different incident angles of the material, and then we will see how the emissivity works in different directions. Okay. And then also with the possibility to heat up the sample, this is very important for some of the materials and also especially for some black body reference. And with such accessories, you are able to heat up the samples from 50 degrees to 400 degrees. Yeah. And this is, as I said, very important for the emissivities of the rooftops. Okay. And another very interesting topic at the moment is that more and more manufacturers, they are trying to put such a passive radial cooling materials on top of our jackets. So especially for the advanced outdoor jackets on the textile, we are able to now make some coating on top of the textile. And then if you see, we don't do any coating on it. Yeah, we can have this low emissivity in the mid-infrared range. But now if we put such a passive radial cooling coating with such a designed structure on top of the textile, then we can get much higher emissivity. And this, as I said, this is the information or improvement that with such a coated textile on the jacket, you are able to bring more heat out from the jackets. And I think this is a very promising applications for our human daily life. Yeah. And as the time is very limited today, I won't go further details with this textile studies, but here I listed very interesting articles for you. If you're interested in, you can go for these papers and read later in details. But what I want to deliver to you today as information is that this passive radial cooling materials is a very hot topic now. And this is also a very promising technique that you can reduce the energy consumption dramatically. Yeah. Okay, so this is the first part of my presentation. If you have any questions, you can put the questions into the chat. And now I will switch to my second presentation. Okay. So my second presentation is about the hydrogen storage by means of catalytic hydrogenation. And by using the FTIR, we can study the mechanism of such a process. And I think this is also it will be a very interesting topic for you today. So here I get this picture from the US government website of the Energy Department. And there they have summarized the different ways of the hydrogen storage. And the common used ways for the hydrogen storage nowadays is, first of all, physical based. This is very often seen as a compressed gas or cold or cryo compressed containers or liquid hydrogen. But actually, such a way is quite expensive, and also energy consumption is quite high for such a physical way. So I think more and more people are researchers. They are now moving to the direction of the material-based uh, hydrogen storage. And there are also five branches for such a material-based storage method. And here I would introduce first for the liquid organic topics. And here, as the example here, the toluene and the corresponding methyl cyclohexane material is very hot at the moment because this material is have several advantages. So first of all, they are low toxic. They have low toxicity, and also they have very good reversibility and stability. And also the gravimetric of the hydrogen concepti is very high, and they have vessel hydrogen charge and discharge properties. But actually, because we are using such a liquid organic process, and the catalytic hydrogenation process is involved in such a storage, um, and in the traditional catalytic way, the usage of the pure hydrogen is very necessary. But that means by using the pure hydrogen, it's very high cost. Yeah. And why we should use the pure hydrogen? Because the existence of the CO can easily deactivate the catalytic active side from the metal elements. So actually, there is a bottleneck for such a pure hydrogen use with this traditional catalytic hydrogenation process. And on the other hand, more and more people have the focus to the crude hydrogen, but there is still the big problem because the CO is the main contamination in the crude hydrogen. However, the cost of the crude hydrogen is half of the pure hydrogen. So from the economic consideration, I would say the crude hydrogen has more, let's say, more potential to be the hydrogen storage mediums. But then that means you have to develop our CO tolerant hydrogenation catalyst in this way. Yeah, and this is exactly how the research is going into. Um, um, and as I said, for the traditional catalyst, many often the case we are using the transition metal, for example, platinum. And no matter you are using the single atom size or the nanoparticle clusters, um, yes, we can do the fine tuning of the binding effect of the CO to the metal particles, but to get the better tolerance of the CO. But actually, when you are getting the better tolerance of the CO, you are also getting the weaker hydrogen purification capacities. So therefore, people have to think about another catalysis supporting materials to get a better tolerance of the CO. And here I would like to share you a very nice paper which is published in the Nature Communication 2 years ago. And here they reported titanium oxide supported a biometal cluster on top. And this is based on the nickel element and the ruthenium element. And here they have studied, first of all, the conversion rate of such a catalyst for the towering. And you see, if you have the pure platinum or pure PD, but also this biometal catalyst, with the pure hydrogen, you can always have the very high conversion rate of the towering. But if you have a little bit CO in the system, then the pure platinum or PD, they will not give you anymore the very high conversion rate. Yeah, because of this well-known reason. But if you have this biometal structure on the catalyst, then you can get still very high or very comparable conversion rate of the towering as the pure hydrogen. And this gives you a very promising way to use or to develop another non-transition, non-single particle or nanoparticle cluster catalyst. But now the question is, why such a structure or such a catalyst can have better conversion rate even with the existence of the CO? And this is the task for the FTIR study. Yeah. And as I said, in this nice publication, they have designed a very systematic studies. So where the catalyst is in the reaction dome, and then they have the gas in and gas out controller from the outside. And then on top of this dome, there is a infrared light going into the dome shining on the catalyst and then go out. And by this designing, you can have the information of what is happening on top of this catalyst surface. And this designing is actually reflected to the drift accessory that my colleague Matthias Kessler has shown in his presentation already. So I won't give you any further detail or repeat it again, the details designing of this drift accessory. But what I want to say is that by such a designing, this Harry-Caprimentis reaction dome is the perfect accessory for this research. Okay, and now let's see what they have done. Yeah, so they have done the 3 scenarios of this catalyst measurement. And the first one, okay, they have tried the combination of the ruthenium and the nickel element, but also they have tried the pure ruthenium elements and the pure nickel elements. And you already see a very clear difference in the reaction process. So for the pure nickel, you don't see any absorption of the CO. Yeah, so that means the CO that you introduced with the crude hydrogen into the system will still being around and affect negatively to your process. And with the ruthenium, then you can have the absorption of the CO on the ruthenium surface, but here you have less absorption of the CH and the towering bands. But if you combine the ruthenium and the nickel together on top of the titanium oxide, then you have both the absorption of the CO and the absorption of the CH and the towering. And then in this case, you can have a very clear picture of the mechanism of this reaction. And here, as they show in a very nice way, is that you will see a selective factor of this catalytic process, which means so the CO will go mainly to the Lutetium side. Yeah, when the toluene side will go mainly to the nickel side. And that means even with the existence of the CO in the crude hydrogen medians, it's no problem because the Lutetium will get them. And this collecting of the CO will bring the freedoms for the nickel to do the traditional hydrogenation catalysis process. So with such a combination of two metal elements here, you can have the very good selection rules for the catalytic process. And then, and this material will now be the very promising material for the crude hydrogen storage. Yeah. And why this have to be studied by the FTIR? Because only with the FTIR studies, you can distinguish the difference between the different absorption of the molecules at the different material surfaces. So therefore, I would say that the drift measurement in this case is the perfect tool for that. Okay, and then the second part of this H storage, or let's say the H release mechanism, is about the ammonium boring materials, and this is also one of these 5 segment. And this is the chemical hydrogen, and by the ammonium boring, we can have the very high weight of the hydrogen when it is released. And also it is proved that we can do the very good kinetic controlling by using the catalyst acceleration, and also the hydrogen release will be not at very high temperature, and this is also very good for the energy consumption regards, and therefore this ammonium boring material is also now very often used as a rocket fuel. Yeah, so this material is actually also a very promising materials for the H storage or H release. And this is a publication which is done by the US research group. And they have actually started, first of all, with the quantum mechanical calculation. And although the ammonium boron is a very simple material, let's say, but if you start the reaction, it actually end up with 63 reactions with 45 species involved in the whole process. And this is, of course, not wanted in the real industry use because you want to find out what is the best way or most effective way for the reaction path. Yeah. And in this case, the first theoretical studies bring them to the most promising way as shown here. So it's again very complicated, but this has been proven by the theoretical study that this can be the most effective way. But to prove that, you would also use the analytical tool to monitor the whole processing. Yeah. And then here, if you want to use the tool, the FTIR with the thermal gravity machine is again the perfect tool for that. So here, the main part of the setup is the thermal gravity, and the ammonium boron is inside of the thermal gravity machine. And here you can see the 2 ways. One way is the outgassing coming into the FTIR module, and the other one is going to the quadrupole mass spectroscopy. And with the mass spectroscopy, you're able to analyze the mass difference scanning spectra. And by using the FTIR, you're able to know at which temperature or which heating rate you get what outgassing. from the thermal gravity. And here is simply that they have tried with the ammonium borate material with the different heating rate. So they are trying with the 5 Kelvin per minute, 10 Kelvin per minute, and 20 Kelvin per minute. And they have proved that with the 20 Kelvin per minute, which is very fast heating up speed, and you can get the most effective release of the ammonia, and also you can have the very clear observation of the ammonium peak at the different temperature. And also here, if you are counting at the different temperature stages, you can see that they have 2 peaks of ammonia release at 400 Kelvin and 450 Kelvin respectively. Yeah, and this is also a very nice proof that they have this first stage here. And with this first stage, this material also plays as or play as an automatic or let's say self-catalyst in the process to accelerate the whole process to the second stage. Yeah. So here I just want to give a simple impression for you that the for the H storage or for the H release process, the FTIR machine can be used in a different way. Okay, so that's the second part of my talk. Again, if you have questions, you can put in the chat. Okay. Now I will start with my third presentation.
Rizky.
Yeah. Okay. So as I see the time is running out. Yeah. So I will keep the presentation fast. Okay. So as I said at the beginning, the FTIR machine is not only for the molecular vibration study, it's not only for the material optical properties study, but it's also related to the environment monitoring topic. And here I would like to show you a very nice examples from Bruker, and this is also unique solutions from Bruker. So if we are now talking about the global warming or the climate change, we are often talking about the tornadoes or tsunamis or forest fires and so on. And these are all actually caused by the global warming effect. And here I would like to give you a very short overview of the global warming effect. What does it mean in the statistic? And here is the comparison of the temperature increase. So in the last, from 2011 to 2020, the temperature increase of the whole world is about 1.1 degrees. But actually in the year of 1850 to 1900, the temperature change is almost flat. Yeah, and also why this year period is mentioned here, because the industrial revolution started in this period. Yeah, but as you see, for the earlier industrial revolution, the temperature change is not so dramatic, but within last 10 years, we have suffered a really dramatic change in the temperature. And this is actually mainly come from the CO2 emission, the methane emission, and also the nitride oxide, and also the halogenate gases emissions. And all these emissions of the greenhouse gases is because of the human have too fast industrialization, and we have also too much agriculture practicals, and also we have used too many fossil fuel materials. And now if we let such a situation go on, And then what we can do, we can have at the end of this century is that the temperature will go further higher with around 2.7 to 3.1 degrees. And this means you will have much more often heavy rains in many territories. And also in the North Pole, the bear will not have any good living conditions. And also you will suffer the increasing level of the sea. And then maybe some of the small island will be also facing problems to immigrate to the middle of the land and so on. Okay, but of course we cannot let such a situation go on like this. So many countries, I would say almost all the countries in this planet, they have launched the goal to have the net CO2 emission um, in the next 20 or 30 years. And then this will help to limit the global warming to 1.5 degrees. Yeah. And also here are clear goals from the COP28 meetings last year in Dubai, and there they have almost 200 parties involved, and the goal is quite clearly. That means by the 2030, which is in 6 years, we should try our best to keep away the use of fossil fuels anymore. And we also should triple the renewable energy and double the energy efficiencies. And this is exactly the topic for today. And we also have seen that we have the hydrogen as the clean energy, and also we should have the solar cell, and we should have more electrical vehicles, and so on. And also this passive radio cooling is one of the solutions. But no matter which kind of green technique you are using at the end, there is always the task to monitor the effort, or how good or how bad you have developed this clean energy technique. And this comes back to the topic that all the atmospheric researchers, they have to look at the greenhouse gas emissions in the certain territories. And therefore, there are two biggest organizations worldwide to do this job. And one is called TCOM, and this is the abbreviation for the Total Carbon Column Observation Network. And the other one is called NDAC, and this is the network for the detection of the atmosphere composition change. And if you are looking at the map they published on their website, you will see that these observation stations are almost distributed everywhere, or in the 4 territories of the world, yeah, and also here. But the most important information here I want to deliver is that both TCON and NDAC organizations, they are using the FTIR spectrometer to do such a monitoring. And this monitoring is not done by the benchtop FTIR that Matthias or me has shown you before. It's not Vertex, it's not InVenue, it's the IFS 125 from Bruker. And why this? Because this IFS 125 machine, they can have the very, very long arms in the interferometer, and this can produce the super high resolution, spectral resolution at the end in your infrared spectrometer. And then the next question from your side might be, okay, why do we need such a high resolution for the atmospheric monitoring? The reason is quite simple. So if we understand how this machine works, so here I put a picture for information. So first of all, the source of this spectrometer is not our traditional glow bars or NIR lamps and so on, tungsten lamps. It's the sun. in the universe. Yeah. So the solar light will come from the universe to to our atmosphere and then finally enter into our spectrometer. And here we have this solar checker, which is following the sun and then guide the light into the spectrometer. But if you are looking at the path, how the sunlight is going, then you see the path is extremely long. It's from the 50 kilometer at the top of the stratosphere to the earth, to the ground. Yeah. And then also you can understand that at the ground, our pressure is normal, is the ambient pressure. But if you are going higher and higher to the um, atmosphere, the pressure is also getting lower and lower. And in the infrared spectroscopy of the gas, we understand that with the extremely low pressure in the past, you will have very, very narrow molecular vibration lines from the gas. And therefore, if you want to study from the ground to the top of the atmosphere, you will need a high resolution spectrometer to get all the lines solved. And now if I zoom in all these spectra, you will find more than 100,000 lines of the gas absorptions. But for all these lines, they are actually corresponding to the H2O, CO2, CH4, O2, and N2O, and CO, and so on. And these are all the greenhouse gases. Yeah. And for the mid-infrared range, we can also have these halogen gases available. But no matter in which range, we have to deal with this super high spectral resolution spectroscopy. Yeah. Okay, so this is a very simple idea that how this machine works. And now let's see what is the result from their observation. And this is our monthly updated picture from the TCON website. And if you look at the CO2 emission over the year, then you can see from the 2004 to 2024, over the last 20 years, the CO2 emission is increasing continuously. Yeah, it's increasing continuously. And all this tic-tac shape of the data is the switch of the summer and the winter. Yeah, because in the winter you have less um, photo photo effect from the plant. So then therefore the CO2 is getting higher. But this is also a natural explanation of the um, observation. And there's another CH4 release, and you see that also over the last 20 years, it's getting higher and higher. And then, of course, with the final goal, which I have shown before here, let's see if we can have a turning effect at the graph by the end of 2030 to have lower or flatter or more flat CO2 emission and CH4 emission at the end. Yeah, and as I said, the ultra high resolution spectroscopy is not anymore the benchtop spectroscopy, and the place where this spectrometer is used is not in the lab anymore. So we are very often place this big machine to the containers, and we bring them by the truck or the ship to the middle of the ocean or at the top of the mountain. But also some of the countries, for example, this is the latest news from German government that we have built up a very nice uh, atmospheric lab on top of the Zugspitze. So this is the highest mountain in the Germany in the Alpen area, and there they have a very nice big monitoring lab below this roof, and this big dome is related to the solar tracker, and then when this is opened, the solar light can be guided into the room and then for different measurements. Yeah. And as I also showed you the map, nowadays, such monitoring stations is everywhere in the world. Yeah, and I believe that all the countries, they also put many focus on this topic. Yeah. So what is important that only the broker IFS 125 can be used as a tool for the monitoring, to monitor the greenhouse gases concentration over the atmospheric areas. And we are also the exclusive FTIR machine or network collaboration with the TCON and NDAC. Yeah, and I believe this can be also a very interesting topics for the Indonesia government, because I believe that the Indonesia government is also one part of this carbon zero network. Yeah. Okay, so that's all from my side. Now I'm open for questions. Thank you very much.
Thank you, Mrs. Dan, for your presentation. So we have three titles: the PRC material, hydrogen storage, and greenhouse gases. And in the chat we have I think we have four questions. And the first question from Mr. Budiman. He asked about the PRC solution. He said we have challenges such as low energy density, uncontrollable cooling power, and sometimes the limited sky facing area. Need your opinion and short-term solution for this possibility. I mean, Mr. Budiman said we have a solution for PRC, but we have the challenges. Maybe your opinion, Dr. Dan.
Yeah, I would say the PRC materials is now a very hot topic, but I must admit that this topic is just at the beginning phase. Yeah, because I think the material started in the last 15 years. It becomes more and more popular, but as this gentleman mentioned that, yes, the controlling of the cooling power and how to manipulate the cooling process by using such a material is still the topic. And what I can imagine is that, but of course, this is my personal opinion, that one can develop the changeable or switchable roof on top of the buildings, and this can be the one let's say intermediate solutions for that. But maybe the final goal of this PRC cooling material using is that they should have more fine-tuning structure on top of the material. And this, of course, needs time and effort in the research power to achieve this final goal. Yeah.
Okay, Pak Budiman, ada feedback? Is there any feedback from Mr. Budiman regarding the answer? Thank you, Dr. Wu. Loud and clear, Mr. Budiman said. And for another question from Mr. Sapki from R&D Arara Abadi. Did FTIR can detect the degradation material during the reaction processing?
Yeah. Okay, this is a question without a clear answer because it's strongly depends on how much it's degraded. And FTIR, okay, for this application, we are mainly talking about the mid-infrared. And all the molecular vibrations which are infrared active can be observed. Yeah, but if the change or the degradation or absorption effect is not strong enough, or the amount is not high enough, then maybe it ends up as a noise in your infrared spectroscopy. So the answer is yes if it is strong enough, and no if it is too less. Yeah, but as I said, as long as the material or the molecular is infrared active and the amount is enough, then yes, you can. Yeah.
Mr. Sabki, is there any feedback? Dokter Dan bilang memang selama materialnya masih di region infrared dan memang organik, masih bisa terdeteksi seperti itu. Yeah, Mr. Sabki say clear, thank you. And
Thank you
then,
too.
yes, another question from Mr. Nanang. He said, how are greenhouse gases emission classified as direct or indirect? And how do the greenhouse gas level compare over time? And how are greenhouse gas source identified?
Yeah, actually, this is a very nice question. It's also a very practical question. Yeah. And the solution I have showed you with the IFS 125, this is actually the overall greenhouse gases in the whole atmospheric environment. And this includes the direct and indirect emissions of the greenhouse gases, because we are looking at the whole range, and also we are looking at the average effect at the end. Yeah. So with this TCON analysis or NDAC analysis, they are looking at everything. Yeah, no matter it's indirect or direct. But there's also another more portable solutions from Broca. It's the EM27 SUM solution. And this is a smaller spectrometer with a smaller solar check on top of the spectrometer. And we can bring this machine to the different locations. And we can also place this machine, not only one unit, but many, many units around the city or the industry areas. Because I can understand the original from this question is that some of the greenhouse gases are dramatically released in the heavy industry areas, or yeah. And to monitor these areas, you will need a localized solutions. And in this case, this EM20 SUN from Bruker is more useful. And we have, if you go to our Bruker website, you can see also videos or publications about these portable solutions. And we have several nice campaigns in Tokyo and in Paris and in Berlin, because all these big cities, they have more than 10,000, more than 10 million people living there, and also it's really crowded cities, and also it's the heavy, let's say, industrial developed areas. And there we have this campaign for 6 weeks or even half year, and to see how the industrial work, how the human activities, and how the seasons, and how the wind and the weather conditions affect all these emissions of the greenhouse gases. Yeah.
Okay, Mr. Nanang, is there any feedback about the answer from Dr. Dan? Clear. Okay. Mr. Nanang said it's clear, the answer. And the last question is from Mr. Adrian Sah. He said, speaking about EHE monitoring is susceptible to few problems since it's always difficult to infer the contribution of individual source for the total GHG measurement. Also, the variation in pressure, temperature, and relative humidity can negatively impact the accuracy of the measurement when the sensors are not calibrated for the condition. How your opinion about this? Okay, about the instrument, the accuracy of the instrument because so many affected the environmental affected also to the measurement.
Mhm. Yeah, this is also a very good question, and this is also very often discussed in this field by the scientists. And actually, this is also the advantage of the ultra high spectroscopy because with this high resolution capability of the spectrometer, you can have all the lines detectable at different pressures. And the scientists, they are able to extract the different absorption lines from the different height. Yeah, because if you go higher and higher to the top of the atmospheric, the pressure is getting lower, and then that means the gas absorption lines, they are also getting narrower. And the narrower the line is, then the high uh, levels of the altitude is for this emission. And for example, if we are talking about the humidity, it's about the water vapor. And for the water vapor, it's almost accumulated in the height of, let's say, 2,000 meter or 3,000 meters at this range. But if you are going to higher and higher, you're able to see the, let's say, almost constant or static, stable contributions of the humidity at that level. And these are all distinguishable from the spectroscopy because the lines of the different height is showing at the different places and also with the different widths. So in this case, the scientists, they are able to draw a line as a function of the height of the monitoring. And then they can clearly distinguish what is the humidity distribution at which height and what is the CO2 distribution at which height. And this also is our site approval, uh, or let's say the friend of EM27 Sun. Yeah. So for the localized analysis. Yeah.
Mr. Ardiansa, is there any feedback regarding the answer? So memang sudah dikalkulasikan seperti itu ya Pak, perbedaan mengenai suhu lingkungan. Makanya alatnya pun tidak di kondisinya tidak di udara terbuka, tapi memang instrumennya di dalam. Hanya memang sumber cahayanya memang dari sinar matahari. Okay, thanks. So the last, I guess, yeah, the last question from Mr. Harris Polinema. Is it true that AFTIR analysis result affected by the vibration?
Okay, if you mean the vibration of the environment, I would say no, because this is not actually a topic for the FTIR benchtop machine or even the portable machine, because, for example, we have this rock solid interferometer, and this cubic corner design of the interferometer mirrors. Um, it is able to guide the light exactly in the opposite direction of the incoming direction. Yeah, because of this cubic mirror designing. And even with the traditional design of the interferometer, like this Michelson, we are still have this alignment, true alignment techniques, which can let's say, adjust the vibration induced differences, yeah, at the end in the spectroscopy. And no matter which kind of interferometer you are using, we still have another key solutions in the analytical process, because we are not only measuring the sample, but also we are measuring the background. So background means that you don't put anything into the beam path. Yeah, so you're measuring the empty chamber uh, in the FTIR spectrometer, and then this gives you our in-time status of the spectrometer, and then immediately afterwards you are measuring the sample. So even there is some change in the environment or caused some side effect, no matter from where, you are able to see it at the end. Yeah, so you are able to eliminate from the background subtraction. Yeah, so this is no problem.
Mr. Nanang, is there any feedback? Sorry, Mr. Haris, is there any feedback? So, tidak ada pengaruh ya Pak, ada vibrasi di luar terhadap pengukuran FTIR seperti itu Pak. Okay, I think the question is done. Hopefully, is there any question that I'm not answer yet? Let me check first because I don't want to miss for the question. Wait a minute. Okay. Oh, Mr. Nanak have two question, different question about GSG, right? Another question he would like to know about how the GSG emission monitored, and can we control the amount of the greenhouse gases?
Yeah. Okay. For the greenhouse gas emission monitoring, I would say for the TCON and NDAC, they are monitored afterwards. So actually, they are doing such experiment not right after the industrial activities, but they are measuring at also the area where they put this machine is not in the center of the industrial area or the human activities condensed areas. So they are rather put this into the very clean areas, and the reason for that is that they don't want to have such a let's say, time-dependent influence on their data. They rather want to see the total contributions over the time and over the big areas. Yeah. So therefore, the locations of such a big machine is not usually in the center of the city. It's rather in the clean mountains or where the human activities is much less. Yeah. But the third question, how can we control the amount of greenhouse gases? This is, I think, a very, very big topics that the whole human have to solve. And I would say, yes, I think there's no clear answer for that because nowadays I think although the electrical vehicles are well developed, but I think a major part of the vehicles or traffic material tools are still based on the fossil fuel. Yeah, and this is the main part of the emission, the greenhouse gas emission contribution. And but we should put our hope into this clean energy like hydrogen, like solar energies and the renewable energies and so on, and try to use less and less fossil fuel in the future. And also we should think about how to improve in the side effect brought from the fast industrialization. Yeah, and this is I think for example, for the industrial level catalysis, this is also a big topic now. And I think many chemical industrials, they are now trying to find the fine-tuning process of the catalysis process just to get a little bit higher efficiencies. And this also, as Matthias Kessler has presented in his PPT, that the conversion of the CO2 in the industrial level is now also a big topic. Yeah, so we indeed have different ways to decrease or reduce the amount of greenhouse gases, but I think so far we have to live with such a situation, and we have to develop ourselves for different new techniques to make the change. Yeah.
Yeah, thank you, Dr. Dan, for the answer. I think all the question has been answered. Finally, now we have reached the end of the presentation. I would like to say thank you a lot for Dr. Kessler and Dr. Dan for all the great presentation, and for the audience. Thank you so much for the active participant also. And from me, Rizkia and Fiti Novatek Integra Solusindo, we have to thanks to all of you. And please continue to Mrs. Dewi to continue the session.
Okay, thank you very much for Dr. Matthias Kessler and Dr. Danwu, and also Ibu Rizkia. Thank you very much for your guidance during our main session. Well, as I mentioned before, committee has also prepared some door prize for the best participant with the best question. So we are pleased to announce the winner of our webinar door prize. The first one is Mr. Ardian Shah from PT Indah Logistik. The second one, Mr. F. Budiman from PT Datanet Indomedia. And the third one, Mr. Nanang from Adiagraha. We will please contact us via direct message in our Instagram event official, so we can get your address and we can send the prize. Okay. Once again, congratulations to all winners. Well, this is the end of our webinar, and allow me to invite Pak Agustan from IFE to close this webinar officially. Please, Pak Agustan.
Thank you, Mbak Wiku. I would like to thank for Dr. Kessler and Dr. Danwu for very interesting presentation today. And of course, thank for Brooker support for our webinar series. For information, Indonesian Fuel Cell and Hydrogen Energy Association will hold a global hydrogen ecosystem summit and exhibition in Jakarta in April 2025. This summit will invite national and global hydrogen players, and of course, Indonesian government to talk about Indonesian hydrogen policy for the net zero emission program. We would really appreciate for if broker and all participant webinar today, if you can come my submit in next year. For more information, please visit Indonesian Fuel Cell Hydrogen Association website or social media. Finally, I would like to thank for all participants and today, and I think this webinar series in the last one of this year. So I say see you next year. Thank you.
Okay, so thank you all participants, speakers, and moderator, and also our sponsors. Hope we can meet again in next event next year. See you.
Thank you.
Thank you and see you.
Okay, thank you, Dr. Danu. Thank you, Ibu Rizkia.
Thank you very much.